All right, so let's do some analysis of covariance. This is based on a study, real study, master's thesis of a student I helped who was looking at folks with trichotillomania, that is the compulsive uh, desire to recurrently pull out their own hair. And initially, a group of just undergraduate psych majors who were available for comparison. So, going through the process, we got two groups. We got trichotillomania group, and we got another group that is non-trichotillomania, which consisted of undergraduate students at the university. And she was looking specifically at family expressiveness. And so the hypothesis here is, let's see, the goal anyway. Are people diagnosed with trichotillomania less able to express positive, negative feelings about their family of origin than people not diagnosed with trichotillomania, as indicated by a lower score on the FES expressiveness subscale? So let's see what we can find out. So step one is or question one is how many levels of study group are being compared in this ANOVA? There's two. So people with trichotillomania and people with no trichotillomania. Is the research hypothesis above two-tailed or one-tailed? Well, specifically, let's say diagnosed, uh, less able suggests a one-tailed. They're saying trichotillomania group should be lower on this family expressiveness. This is going to be one-tailed. And we got to fill in the hypotheses then. So it's kind of like a t-test because there's only two groups, but we're going to use ANCOVA and ANOVA to answer it. So our research hypothesis goes here. Research hypothesis is that group one, that is our trichotillomania group, is going to be less than the other group. And our our null hypothesis, therefore, is all other possibilities, which is, let's see, all other possibilities greater than or equal to. So I will fill in greater than or equal to. Why is X bar one our trichotillomania group? Because they are group one, X bar one. So they're expected to be lower on that mean. So we're going to check the normality assumption that's required for doing ANOVAs and all the between groups designs. So to do that, you are to go to Analyze, Descriptive Statistics, and Explore, and put Study Group as your factor and Family Expressiveness as your dependent. And then click OK. You get a bunch of stuff out of this. So it's asking specifically what is the skewness statistic for the trichotillomania group. Trichotillomania group, family expressiveness, skewness statistic is 0.664. 0.664. Non-trichotillomania group, right down here, skewness coefficient for them is negative 0.466. Negative 0.466. Does it appear that does the data appear to be the normality assumption? That is either one of these absolute value of 2 or bigger? If so, you violated it. If they're less than absolute value of 2, you've met it. So I would say yes, these are both less than the absolute value of 2, so we have met that assumption. So now what we're going to do is do a ANOVA, where we just compare the two groups on their family expressiveness without any covariates. And this is for didactic purposes to show you how it changes when there is an ANOVA. So to run this, we go to Analyze, General Linear Model, and Univariate. In the univariate window, we've got to take family expressiveness and move that to our dependent variable box. And then we have to move a study group to the fixed factors box. And then we got to pick some options. So under E means, where you get estimated marginal means, you need to move study group over to the display means for box. Click OK. Under the plots, We are supposed to go ahead and move a study group to the horizontal axis. So there we go. Click Add, and then click Bar Chart and continue. Then finally, click the Options button. And under Options, you have to get Descriptives and Homogeneity Tests. And then click the Continue button to continue. So finally, once everything is set up, click OK to run the actual analysis. And that's it. We've now run the ANCOVA. So let's take a look at what questions we got to answer. What is the mean and standard deviation for each level of the independent variable, round to 2 decimals? So over here in the descriptive statistics box, we've got trichotillomania and non-trichotillomania. We've got mean and standard deviation, boom, boom. So the mean trichotillomania is 2.93. Standard deviation to 2 decimals is 2.72. So 2.72. For non-trichotillomania, that's here, 5.49, 5.49. And standard deviation is 2.41. So, I mean, looking at these two means, it sure seems like the trichotillomania group is lower on family expressiveness. The question is that a meaningful difference or not? We'll get to that in a sec. So now we have to check the homogeneity variances assumption for number 5. And so to do that, we find a table called Levine's test of equality of variances. We find the row that's called based on mean. We go over and we look at the sig. So the question is, using alpha of 0.05, does the data appear to meet the homogeneity variance assumption, i.e., is Levine's based on mean sig greater than 0.05? That's 0.285 is greater than 0.05, so we have met this assumption. So yes, we meet the assumption. Finally, we got some decision rules for doing our actual, excuse me, our one-way ANCOVA. So we go to this table called tested between subjects effects. We have a one-tailed hypothesis. So to fully reject a one-tailed hypothesis, 2 requirements are the sig divided by 2 is less than 0.05 for our independent variable. So the between groups row. And the sample means differ in the hypothesized direction. So let's take a look. There's study group, that is our between groups row. Our sig divided by 2, less than 0.001 divided by 2 is still less than 0.05. So it's statistically significant. Do the sample means differ in the hypothesized direction? So what do we know at this point? We know that the two means being compared here, family expressiveness for those who have trichotillomania or not, are significantly different. Let's see if they differ in the correct direction. 2.93, 5.49, it was hypothesized up here that the mean would be lower for those in group 1, those with trichotillomania, and indeed these two things are significantly different, and the trichotillomania group is lower, 2.93 versus 5.49. So I guess I could have looked here too. So question is, using alpha 0.5 decision rules above, are the sample means significantly different from each other? Yes, they are. Are you able to fully reject the null hypothesis? So that's asking, are both of these things met? The answer is yes, we can. Why? Well, let's see. Sig divided by 2 is less than 0.05, and trick is lower. I guess trick mean is lower. There we go. That's better. Or trick. Okay, whatever. Trichotillomania group was lower on family expressiveness at 2.93 versus 5.49. So to calculate the proportion of variability, we've got to do the following. We've got to calculate the sum of squares for the IV. So I'm going to do a little formula up in this box just to make it obvious is for study group 146.94, 146.94. We have to divide that by the sum of the sum of squares for the IV plus sum of squares error. So that plus that. I'm just going to pull up the calculator really quickly to do that. So the numbers we need are 146.944, 146.944, thus the error is 580.044, 580.044. I get 726,988. So I'll put that here. And we just need to divide those two things now. That is the sum of squares for the IV, that right there, plus the sum of squares total, which is sum of squares IV plus error. So survey says 146.94 divided by 726.988 is 0.202, a bunch of change to 2 decimals is 0.20. So I'll put 0.20 there. All right. Next question. We gotta put it put the results of that ANCOVA in APA format. I'm going to cheat a little bit and copy this over and just fill stuff in. So I will paste that in there. We need our degrees of freedom between. Degrees of freedom between right there is 1. Degrees of freedom within, which is our degrees of freedom error, is 88. Here goes Dagny walking downstairs. Our actual F value is 22.93, and our P is less than 0.05. And this used to say ADA. I'm not quite sure what happened here, so we'll fix that. There we go. And actually, this is supposed to be italics, and this is supposed to be italics too. Our ADA squared we calculate right here is 0.20. 0.20, and that is in APA format. All right, next thing we got to do is fill out this ANCOVA summary table. So that all comes from here. Note, we don't care about a couple of these rows. I think there is a way to highlight certain rows in here so we can focus on them. Let's see if I can figure this out. Study group, and A, and that is totally not what I wanted to do. That did not work out as planned. So let's see if I can't highlight study group a little bit better than that. It's doing multiple rows. And anyway, I give up, but there is a way to highlight a row so it's easier to focus on. Oh, that's it. Let me try one more time. So if I highlight the study group row, I got it all. I think you can change this to yellow. Let's see if that works. Oh, it did. Totally cool. And error we need as well. So I will highlight that one as well. You don't have to do this. This is just because that didn't work anyway. This is just because it's easier theoretically to see things if you highlight them. All right, there's our 2 rows we care about, and then we got to add things up to get the total. So our sum of square for study group is 146.94. Got it just to 2 decimals. It's 1 degree of freedom, 146.94. Our F value is 22.29 with the star, getting that from right there. And our ADA squared we calculated above is 0.20. For error, 580.04. So we're on this row now. Our degrees of freedom is 88, and our mean square is 6.59. And finally, we got to add these guys up. So that's actually we did that up above, didn't we? 726,988. I'll re-add it, but 146.94 plus 580.04, 726.98. So 726.98 is what we put there, and these 2 added is 89. That's our ANCOVA summary table. Scooting along, given the null hypothesis was rejected, and there are only 2 groups, so no 2 key post hoc test is required. Which group had the lower mean family expressiveness? We already established this, that the trick, oops, trick group had lower family expressiveness than the non-trick group. How do we know that? It was statistically significant. We already established that by looking at the two means to see trick is lower than non-trick. Interpret the meaning. What do they tell us about whether and if so, how the independent variable affected or was associated with differences in the dependent variable? So, gosh, a couple ways to do this. I guess here's how I would do it. I would say um, persons diagnosed with trick came from families with less, uh, um, where they were less able to express emotions. Oh, no, not expressive. They express emotions. And I'll go ahead and throw the mean in. That not 100% necessary. 2.93. Then persons not diagnosed with trick. And their mean was equal to 5.49. And I just get crazy up in here. I'll get all APA on this. All right. Persons, actually, I guess that's people. Diagnosed with trick came from families where they were less able to express emotions, and people not diagnosed with trick. Something like that. That's the meaning of it. So, true story, this graduate student turned this in to the committee, and the committee said, you know what? You found, she actually found that for every subscale of the family expressiveness inventory that the trick folks were lower. So they said, you know what? You compared folks with trick who tend to be older and female to a bunch of undergraduates, which even though it's psych, so it still tends to be like 80+% female, but there's more men and they're all a lot younger, males and females. So maybe some of these differences you got are just age and gender differences. Um, why don't you see if it's possible that age and sex are confounders in your study? So sent her back to go do that. So that's what we're going to do now is test in order whether age and sex are potential confounders in her study. Remember, for a variable to be a confounder, it should be associated with the dependent variable, and it should differ as a function of the independent variable groups. So that is to say, um, age and sex, are they correlated with family expressiveness? And age and sex, do they significantly differ across folks who have and don't have trichotillomania? So we're going to try to establish that. So first thing is the average age different for persons in her study with and without trichotillomania? Let's find that out. We're going to do a t-test to do that. So we'll go to Analyze and down to Compare Means and Proportions. And I can't see because my picture's in the way. Of course, Analyze, Compare Means and Proportions, Independent Samples t-test. Study group is our grouping variable. Click that little define button, and 1 and 2 are the two groups, the numbers for the groups. 1 and 2 we want to compare. Nope, not family expressiveness. Age is our test variable, so throw that in there. I don't think there's anything under options or bootstrap that you want. So looks like that. Yes, click OK to get a t-test. So this is a t-test comparing the average age of folks with and without trichotillomania. Scooting over here, you can see those with trick on average were like 38. Those without, on average, these are, I guess, undergrads were about 20. Wow. So they were almost twice as old, is another way to think about that. Let's go through the questions. Is the research hypothesis about two-tailed or one-tailed? I don't remember if there is a statistically significant age difference between the groups. That does not say whether one group is older or younger, so that is a two-tailed hypothesis. So two-tailed. We're just seeing if it's associated or if age differs between the groups, right? So the only thing, we only have one way to write these hypotheses. So our alternative hypothesis here, which comes from our research hypothesis, is that the means, that is the average age of the two groups, is going to be not equal. So I will go ahead and copy that and paste that here. And that means our null hypothesis is all other possibilities, which is they are equal. So there. So if we reject that, we will assume for the time being that there is a difference in the average age of folks with and without trichotillomania in her study. So we got to fill in the means and standard deviations for the APA write-up. And so those are right here over on t-test. The average age for those with trichotillomania was 38.33. The standard deviation, so I go down, is 10.83. Average age for non-trichotillomania is 20.22. And standard deviation for them is 2.98. All right, using alpha 0.05, does it appear, does the data appear to meet the homogeneity variance assumption? That is Levine's test for equality of variances, sig greater than 0.05. So there is Levine's test for equality of variances sig, and that is less than 0.05, not greater than 0.05. So no, these data do not appear to meet the homogeneity of variances assumption required for independent sample t-tests. So what's that mean? Do we give up and go home? No, it means we can't assume equal variances if that is less than 0.05. So we drop a line to the equal variances not assumed line. That's what we got to do. So doing that, let me just sort of scooch and see what's over there. Let me shrink this a little too. There you go. So again, because this sig is less than 0.05, it means we violated. The question is, does the data appear to meet? No, it does not. So should we use equal variances assumed or equal variances not assumed? We are going to use the equal variances not assumed line of results. So I'm going to copy this and paste this over here. And okay, let's keep going. So to reject a two-tailed hypothesis, the only requirement is that significance two-tailed P is less than 0.05. So on this row, we go to significance two-tailed, two-sided P. That's what it's called. That sucker is definitely less than 0.05. Excuse me. So indeed, are the sample means significantly different from each other? Because that is less than 0.05, we would say yes. There is a difference in average age between these groups. Are you able to fully reject the hypothesis? Yeah, because there's only one requirement. That is, that sig needs to be, two-tailed sig needs to be less than 0.05. So yes, we can fully reject the hypothesis. Why? It's sig two-tailed is less than 0.05. Great answer. What is the difference? I guess you could calculate that by subtracting these, or there's a column here that shows the mean difference, 18.11. So on average, they were a little over 18 years different, which had the higher mean. That is the trick group. So trichotillomania group was 38 on average versus 20 for the undergrads. So I'm just going to put the trick group. We got to calculate our omega squared, and that's a little complicated. So I will put the formula in here. We need t squared minus 1 up top. T's right here. We got to square it. So I'll pull up calculator and do 10.818 squared And I'm just going to round that as 117.03. So 117.0, oh, minus 1. Minus, don't forget the minus 1. Minus 1 is 116.03. 116.03. And that's going to be divided by something on the bottom. A bunch of stuff, actually. So let's just fill it in. First of all, t squared again on the bottom. So let's go ahead and do t squared again. 10.818 squared is 117.03 again. And then we have to add the sample size for group 1, sample size for group 2, and then subtract 2. So there was 45 and 45, so it's plus 45 plus 45 minus 2. It's 205.03. So 205.03. Hope we got that right. So let's see if we get something reasonable. 116.03 divided by 205.03. You get 0.5659, round that to decimals is 0.57. Big old difference. So about 57% of the variability and ages can be accounted for by whether they're in the trick group or the non-trick group. That's a little nutty. So let's go ahead and fill in our T. T, degrees of freedom right here is this rounded to the, please tell me I tell you this, where degrees of freedom is rounded to the whole number. So round that to 51. So degrees of freedom. And why you make my T big? T 51 degrees of freedom is equal to a T value right there of 10.82, comma, P is less than 0.05, comma, and I'm just going to be copying this over because I ain't got time to go look that up. Omega squared, but I will bold you, and 12. There, everything's 12. I don't know what I did here. Yeah, 12. Omega squared right there, 0.57. We just calculated that. That is, if I go ahead and go all APA crazy up here, this is our T result written up. Let's see. Wait, why does this say 51? Oh yeah, sorry. Yeah, we had the equal variances not assumed, so we had to round it. Interpret the meaning. What do they tell us about weather, and if so, how the independent variable affected was associated with differences than dependent variable? Well, what these results tell us is that the trick group was older, 18 years on average, than the non-trick group. Where do we get that from? Well, statistically significant. There's their average ages. So because it's significant, we know these two ages are significantly different. Who's older? Who's got the higher mean? Well, the trick group was 38, non-trick 20. So, I mean, you could have put the two means, said the trick group is 38.33 on average versus the non-trick group is 20.22. Whatever. I mean, I just chose to use this mean difference and say like they're 18 years. The trick group was older, 18 years on average than the non-trick group. So age differs between those with and without trick. The next thing we got to do is test for sex confounding. So run the appropriate statistical procedure to determine if there is a statistically significant difference in the sex distribution of the groups using alpha 0.05. Hint, chi-square test of independence. Hypothesis is there a significant difference in the sex distribution of the study groups? And if so, which group had a higher percentage of females? Well, to do this, because sex is a dichotomous nominal variable, we're going to use chi-square. To get to that chi-square, we go to descriptive statistics and down to crosstabs. There is no chi-square test of independence menu function. And I give you some specific stats here. Tell you that move sex to the rows box. This is just so we all match. And study group to the columns box. Cool. Select the displayed clustered bar chart. So that's down here. Click statistics. Okay. And then under statistics, select chi-square and collect phi in Kramer's V, which is right there. I think that's it. Click continue. And then under cells, you always got to pick whether, well, first of all, I tell you to get the expected. So let's click observed and expected we're getting. But I tell you specifically to get the column under percentages. You just got to pick, do you want columns or rows? But also tell you to get the adjusted standardized, so which is the follow-up test for this particular stat. In case it's significant, they tell you like where those differences are. So click continue. Little note here, sometimes rows better. In this case, I'm telling you, go ahead and do column. Then when you're done, click OK to run your chi-square. So here's our chi-square analysis. Fill in the null and alternative hypotheses below. So remember, these ones don't use math to define the hypotheses. So the alternative hypothesis is that there always is some sort of relationship between the variables. Null is that there's not. So the alternative might be, for example, it's got to be something like the sex distributions differ between those with and without trick, which is probably what I'm going to say. So the distribution of sex differs between people with and without trick. That's as simple as I can think to write that. So that says they differ. So the null is that going to be that they don't differ. I'm going to save a little bit of time, paste this up there, and say does not differ. Does not differ between people with and without trick. There's our hypotheses. So then we got to fill in some percentages here. So those come from this table up here. So for people with trichotillomania, what percent are male? So trichotillomania, what percent are male? This is the percent within study group, by the way, which the columns that do 100%, each column. That's how you know you have column percents. So it's 6.7% of the trick group was male. 93.3% was female. For the non-trick group, it was, 24, almost a quarter, 24.4% was male, and 75.6% was female. Whoa, those seem not the same. Let's see, use an alpha of 0.05. Oh, wait, decision rule. To fully reject the chi-square test of independence, null hypothesis, the only requirement is that the asimp sig two-sided is less than 0.05. So, excuse me, using the Pearson chi-square row, scooting on over to our asimp sig, is that less than 0.05? Yes, sure is. So using should the null hypothesis be rejected? Yes. Why or why not? Well, because asimp sig is less than 0.05. That's why this sig right here, less than 0.05. So we've got to calculate our proportion of variability. So that's a little formula again. So I'll pop it in here. I do think in this case, you can actually use Kramer's V down here. So let's see what we get if we actually tried this formula to get the proportion of variability in the frequencies accounted for by relationship between the variables, that is study group and sex. So how are we going to do this? So we need the square root, which I don't have a fancy little symbol for that. So I'm just going to put, we need the square root of chi-square. So that's just chi-square. It's not chi-squared. It's already squared. So find our chi-squared value. It's right here, 5.41. And that's going to be divided by, it goes on the bottom, n times the minimum, so the smaller of the number of rows minus 1 or number of columns minus 1. So you don't count total when you do this. You just count the number of actual values. So there's 2 columns, there is 2 rows. So either way, -1, it's going to be either 1 or 1. So the smaller is 1. So n times 1. Well, what's n? N is right here, number of valid cases, so it's 90. So on the bottom of this, we put 90. So we need the square root of 5.41 divided by 90. So you got to remember to do this first and then square root. So let's see what we get and see if it matches this 0.245. So get the calculator up. It's 5.41 divided by 90 is that thingy. Let's get the square root is 0.245. And so that'll round up 0.25, 0.25. And down here, 245, which will round to 0.25. So that is our proportion of variability. So 25% of variability in the participants' ages can be accounted for by whether they're in the trick group or the non-trick group. So now we got to fill in a chi-square, and I'm going to go ahead and cheat a little bit and paste it in there, and I'll bold it just to be legit and make it 12. All right. So we got to get the degrees of freedom. Well, get that out of the way. Degrees of freedom is 1 right there. And I don't know why it's doing that. There we go. Our n is the total sample size. Again, that's right here. There's 45 and 45, so 90 total. Our actual chi-square value goes here. Chi-square value is 5.41. So I'll type 5.41. Our p right there is less than 0.05. And our v we determined right there is 0.25. 0.25. So post hoc direction and magnitude of differences. So whenever a chi-square test of independence is significant, you then have to look in each of the cells. This cell, that's a cell, cell, cell. So it's all crosses of trick males, trick females, non-trick males, non-trick females. You look at these things called adjusted residuals and find anywhere where the absolute value is 2 or bigger, you know that cell is funky. If it's a negative, there was fewer in that cell than expected. If it's positive, there was more in that cell than expected. Now, it's a little bit redundant because, for example, this says there were fewer trick persons who were male and more trick persons who were female than would be expected, which if you go down here, you find the flip of that. There's more trick females and fewer trick. Whoa, God, I said that wrong. Start this again. In the trick group, there was fewer males. And there, yeah, I did say that right. But if they're not, oh, here's where I messed up. The non-trick group, there was more males than expected. In the trick group, there was more females, fewer males. So it sort of works out that way when things are dichotomous. So we just have to kind of summarize this. So interpret the meaning of the results. What do they tell you about whether there is a significant difference in the sex distribution of the two study groups? And if so, which group had a higher percentage of females? Well, first of all, yes, those two variables, we rejected this null hypothesis that the distribution of sex does not differ between people with and without trick. So we conclude the distribution of sex does differ between those with and without trick. We want the specifics down here. I would say, like, I'll just pick the trick group as a way to do this. There was fewer males, more females in the trick group. The question is, which group had a higher percentage of males? Okay. Actually, let's just answer the question. What do they tell us about whether there is a significant difference in the distribution of the two groups? And if so, which group had higher? So yes, sig difference. Trick had more females and fewer males than non-trick. That would be a reasonable way to summarize all that. And let me take a break, get a drink of water real quick. All right, for the next step, we've established that the trick group has more females, the trick group is older. Which shows that those covariates differ between the levels of the independent variable. Now we want to show that those potential covariates, to prove that they could be confounders, are they also associated with the dependent variable, that is family expressiveness? So to do that, we're going to do a bunch of correlations. So those are going to analyze and correlate and bivariate. And I tell you a very specific order to do these. So put them in the following order: family expressiveness, age, sex, and then finally study group. Two-tailed is correct. I'm going to click, hopefully I tell you this, two-tailed, right? It's two-tailed hypotheses. We're just checking to see, does it appear that age and sex are related? That's two-tailed. Show only the lower triangle just to make it easier to read this stuff. And under options, select means and standard deviations. Finally, click OK to run a bunch of correlations. All right, bunch of correlations. Are the research hypotheses above two-tailed or one-tailed? They are two-tailed. Why? Because does it appear that age and sex are related? Okay, that's two-tailed. Could be either way. So to write these hypotheses, our alternative is that it could be positive, could be negative, but it's not equal to 0. Our null hypothesis, therefore, is that they are equal to 0. All right, to fully reject two-tailed hypotheses, the only requirement is sig. Two-tailed is less than 0.05. Let's fill some stuff in and throw some stars up in here too. And see what we got. So age is right here. Age and family expressiveness. 1 stands for family expressiveness. 2 is age. 3 is sex. That's what all this means. So that is negative 0.45. And that gets a star because sig's less than 0.05. Just going down the line, negative 0.18, no star. Down the line, 0.45 with a star because it's significant. Scooting over, age and sex is 0.17 and does not get a star because that's not less than 0.05. Study group and age is negative 0.76. That gets a star. And then finally, 3, which is sex with study group, that is negative 0.25. And that gets a star too, because sig is less than 0.05. So that's just, excuse me. Oh, Lord, let me get a drink again. Oh. All right, I'm back. Let's keep going. So, overall interpretation of the confounding analyses. Interpret the meaning of the results of all the confounding analyses. Well, let me back up a sec. So, the question we were answering on this particular subset here is, does it appear that age and sex are related to family expressiveness? Family expressiveness is column 1. Age, yes. Sex, no. So age was associated with family expressiveness. Those are older, so negative. So as one goes up, the other tends to go down. So older persons tend to have lower family expressiveness. Sex, this is not statistically significant. So we would conclude that no. Whereas age was related to the dependent variable, sex was not, at least not significantly. So now, interpret the meaning of the results of all the confounding analyses. Does it appear that age and sex are potential confounders, and that differences between the study groups on these variables might explain her initial findings that people diagnosed with trichotillomania were less able to express positive and negative feelings about their family origin than people not diagnosed with trichotillomania. So I think the way to approach this is the two variables separately. So I'm going to say age. And I'm going to say sex. So let's see. Age did differ between the groups. So the two criteria for being a confounder is it differs between the groups and it's related to the dependent variable. So I'd say yes, related. What's the question here about their family, not diagnosed? Uh, it's so yes, differed between the groups and related to the DV. That's the simplest way to say that, I think. And then for sex, I would say, I mean, it differed between the groups. There was more females with trick, but sex isn't significantly associated with the dependent variable. So I would say no or probably not. Something like that. Why can't it be a confounder? Well, it differs between the groups, but is not significantly related to the DV. So it cannot technically be a confounder in this study. So the age definitely could account for our findings. Sex, probably not because it's not statistically significant. So, regardless, she went to her committee with these results, and they said, "Well, you got like trick people are older on average, and they do have more females, so maybe you should adjust for those." And that's where ANCOVA comes in. You can redo, asked her to redo her ANOVA analyses, but instead, first adjusting for differences between the groups in their age and sex distributions and using those to adjust their family expressiveness scores and then comparing persons with and without trichotillomania to see if they significantly differ. So we're going to go ahead and do that analysis. It's not hard if you have an exited SPSS. All you got to do is go back up to Analyze, General Linear Model, Univariate, and then we have to, all this stuff's already set up, family expressiveness, study group, but we have to take age and sex, and we have to move them into the covariance box. And then under plots, let's just make sure that's still good. Study group is still there. It's still a bar chart. Estimated means, study group still there. Options, still got descriptives and homogeneity tests. So those are still good. So all I got to do is click OK because I haven't exited SPSS since we ran the ANOVA. Click OK, and it kind of bugs me that the numbers just keep on going in here. So it seems like if that ends at 4, I should have started these at 1. I might fix that on your version. So anyway, we reran it, and let's see what we got. SPSS report, standard errors, blah, blah, blah. Sort of knew this. We got to fill in the means and standard deviations of the unadjusted and adjusted family expressiveness means. So for the estimated marginal means, we have to convert the standard deviations, standard errors to standard deviations by multiplying them by the square root of n. Bunch of crap. So anyway, going down here, we need our unadjusted means. That's our crude or raw means for trichotillomania. Those are just up in the descriptive statistics table. So unadjusted mean is 2.93. Standard deviation is 2.71. 2, oh, whatever, right there. I'm going to do unadjusted for the non-trick group. That's 5.49. And standard deviation for that is 2.41. So where do we get these unadjusted means? Well, they're down in a table called estimated marginal means. The means themselves are easy to get, mean and mean. So the trick group adjusted mean is 3.53. That moved up, right, from there. Then I'm going to put the mean in for the other group. Non-trick group is 4 points. That's going to go to 4.90, I think. So standard deviations is where things are a pain in the butt. You got to take the standard error, and note it's the same number, so we only have to do this once. But it's the standard error times the square root of the sample size. That is n. How many were in each group? I think there was 45. There's 45. So we need to multiply that standard error times the square root of 45, which I can't do in my head. So 45 square root is that 6.708, blah, blah, blah. We need to multiply it now. So that is that part. We need to multiply it by the standard error, which is right there. So times 0.495. And that's it. I get 3.32. 3.32 and 3.32. All right. That could have been a lot worse. So now we have to fill in a big old ANCOVA summary table. So that is stuff in here. So I'm going to do the thing where we highlight rows again. So we need age. And I think I did this. Yep. Sex. There we go. Study group. I don't know if that works, but let's try it. And oops, error. There we go. We have to get the total on our own. So, of course it did work. I don't know why that bottom one never works. There we go. All right, highlighted those rows. Make our lives easy. So we're just going to copy these things over. We do put a star on the F if the sig's less than 0.05. So we don't count, put these rows over. We use them to star things or not. And note, nothing here is less than 0.05. So we're not going to be putting stars on anything. So the age, sum of squares, is 19.36. Degrees of freedom of 1. Mean square is 19.36. F value is 2.99. Right there. Sex is 4.52. 1 degree of freedom for that. 4.52 mean square. F is tiny, 0.70 after rounding. No star, no star. Study group, 17.62. Degrees of freedom is 1. 17.62 again. F is 2.72. Oops. No star for you. No significant difference. Error within is 556.50. Degrees of freedom is 86. Mean square is 6.47. Totals, we have to add these to get the total because I don't think any of these add up to that. I mean, 7, no, that one ain't going to work. So let's just add these up. We got 19.36 plus 4.52 plus 17.62 plus 556.5. Oops, 50. I get 598 even. 598.00 and 86,789. 89. Now we do need to get eta squared over here. So not easy. So eta squared, again, there's a formula that's equal to the sum of squares of that divided by the sum of squares of that plus that. So what I'm going to do is get the bottom first. What is this plus this to get that sum of squares total? And that is, let's see, 17.62 plus 556.5 is 574.12. 574.12. So I need 17.62 divided by 574.12. Can I fit that? I can't. 17.62 divided by 574.12 equal to, not quite working, but let's give it a shot. Go 17.62 divided by 574.12. I get 0.03. Or eta squared is 0.03. Using alpha 0.05, do either of the covariates, age and sex, appear to account for a significant amount of variability in the family expressiveness? Whatever. If so, describe the results for the covariate effects. So interestingly enough, neither of these was statistically significant. So the results suggest that no, neither of these did a significant amount of adjusting. So we would say no. Um, it's not what you'd expect given that age differed between the groups, sex differed between the groups, age was related to the dependent variable. You would have thought it would have significantly done some adjusting. Note age was close, it was close to 0.05. Um, it's frequently the case we adjust for things even if they don't meet both of those criteria, just because it's considered good practice to certain things. So we will continue to interpret this analysis, even though age and sex didn't quote unquote significantly adjust things. Do the study groups appear significantly differ on family expressiveness after accounting for age and sex covariates using alpha of 0.05? So study group, not significant either. So do the study groups appear to significantly differ? No. Now, this is kind of interesting though, and this is like real life data. So let me just review before we answer the last one. When, excuse me, we did this as an ANCOVA, we found that there was a significant difference, study hours. Oh, Lord, I gotta fix that. There was a significant difference between the groups, right? So that significant difference was the trick group had lower family expressiveness on average. Where those means 2.93, 5.49. Yet we come over here and we adjusted for age and sex and scooting on down. And the analysis said though neither of those did on their own a significant amount of adjusting. Yet now we no longer have a difference between the groups on family expressiveness. So I don't know how to explain that. Neither of them on their own did a significant amount of adjusting, but sort of together they were significantly adjusting. That would be my guess. But regardless, this poor lady found at this point that, most of the differences between her trick and non-trick group were due to age and sex confounding. So to answer number, I guess, last one here, how would you do this study differently if you're planning to do something similar for your dissertation? Well, the correct answer is something like don't compare um, a trick group which has a different age and sex distribution to a group of undergraduates. Try to get a comparison group that is more similar in terms of age and sex. So something like that is what I would say. Or how would you do the study differently? If I was planning to do it, I would get a comparison group that is more similar to persons with trick. That's what I would do. So last step is to go ahead and write this up using the template that's provided, which of course I don't have up, but I'm happy to bring up for you. Go ahead and write that sucker up, APA template, just to give you a heads up on some of the stuff that's in here. Boop, doop, come on thing. There we go. Nope, keep going. Nope, still not working. There we go. So do note that you filled in a lot of this stuff. So table one, the means standard deviations for age and sex, you actually did fill in way up here when you were doing your covariate analyses. You got your means and standard deviations for age. Those would go here. Same thing for sex. You filled in those percentages here. Those would go there. Table two is the correlations. You did those down here, so you will have to change them. At least one of them is different, just because this was a family. I'm sorry, this is the answer key, so you will have to match these. They're slightly different from the ones that are in the APA template. And then your adjusted and unadjusted means were right here. So you fill those suckers in. Do you note that on figures, you can right click on the figures if you sort of select it right? Somehow there's a way to get where you can right click this sucker. Maybe you got to click on a data point. I don't remember, but somehow there is a way to change the data here. So right click, oh, edit data. You can edit the data and it brings up a little table where you can actually change things. I've already filled in the correct things. Come on, you can open. Make me proud, computer. Now really, edit data. I might have to edit data in Excel, which my Excel takes a minute to open. All right, edit data in Excel. When the box comes up, you can change the underlying data points and the titles. And if you change them to match the unadjusted and adjusted means, it will actually go ahead and update that figure for you as well once you click out of it. So good luck doing that. And hopefully this was helpful. So that's that.